Do you know what we should call this lecture as?
Say that again?
Do you know what we should call this lecture as?
What is this?
Like what we're going to be learning today?
Oh, what should we call this as? Shear force and bending moment diagrams.
Shear.
Right. I'll be writing the topic. And,
What a dumb question to ask. It's not a dumb question.
There are no dumb questions, Mark. Except when I ask.
Why don't you scoot over one more chair, okay? Why don't you go
Mark,
study?
your head's gonna get in the way.
Why don't you go study
Why
some
don't you
shear
kick rocks,
forces in the
buddy?
building? Why don't you
Hey,
just go
Mark,
study
why
some
don't
shear
you head
forces?
out?
I'll head out with you when we go to the lab.
Let's go to lab.
Let's go to
Why
lab
don't you head over to lab? A little early. Awesome.
That is literally you.
Okay, good morning everyone.
Hey, that resale value is
We're going to continue with shear force and bending moment diagrams. And today we are going to see what is called as the graphical method for constructing shear force and bending moment diagrams. Alright, so there will be some growing pains when we look at this particular method as we apply to some problems and so on. But my hope is by the end of Monday, we would be sufficiently proficient in this entire aspect of drawing shear force and bending moment diagrams. And one reason as to why we draw these diagrams is because we want to obtain what the maximum shear force and bending moment values are, so that this in turn helps us calculate the maximum stresses. Before I proceed, is my audio too loud to people? Is everybody okay with the sound? People in the back? All right, okay. All right, so for the graphical technique, I'm going to consider some kind of a general situation, okay? So this is a rigid body, it's a beam, as we discussed last time. Any object that is very long compared to its cross-sectional dimensions. It's pinned at one end, and then I have a roller at the other end. I'm not interested in obtaining these support reactions because we know how to do these. Okay. On this beam, I'm going to consider a plethora of loading situations. One is a distributed loading. Some random distributed loading. This is spaced over a distance, I don't know, whatever it is. And the intensity of this load is W of x. Then I'm considering a concentrated force acting at some location on this beam, whose magnitude is the term capital P. And then I'm also going to consider a couple moment. As you know from statics, you can have couple moments acting on bodies, right? So I'm going to have a couple moment acting on this body at some location along the length of this beam. And I'm going to call its magnitude as capital M naught. Okay. I want to know what the effect of these are in terms of how the shear force changes and how the bending moment changes. Okay. So to do that, I set up my coordinate frame. This is my positive y direction, so you can immediately recognize that the magnitude of the load P is acting in the negative y direction. The load intensity W of x is acting in the negative y direction. What's the sense of the couple moment? Right hand rule tells me that this is going to be pointing into the page. Okay, so this is a clockwise couple moment. Alright. And and my x-axis is along the length of the beam, I'm going to assume that this distributed load spans the following dimension. It's at a length x1 where it begins, and it ends at a length x2, okay? Some length. First, I'm going to consider the effect of a distributed load on the shear force and bending moment values. Okay, so W of x is the load intensity, it's the effect of the shear force and the bending moment. What is the effect of this on that? And to understand this, I'm going to take a very small slice of the beam in the region where the distributed load is acting. Okay, so look at this. Okay, this is a portion of length dx, very small. And I'm going to take the piece and draw its free body diagram. Okay, so this is that portion dx. Then I'm going to have the length of that as dx, marked here. Because I'm cutting it at the right and at the left, I'm going to have shear forces and bending moments on both the sides. And they're going to follow the sign convention. Okay? So I'm going to have a shear force V. Let me call that as V at some x. According to the sign convention, if I'm looking at it from the left side, this is going to take that piece and rotate it clockwise. I have to counteract this by drawing another shear force, which will be at a location V of x plus dx. Likewise, I'm going to have bending moments on both sides. This is M. And on the other side, concave upwards positive according to the sign convention. M at x plus dx. What else am I going to have? I'm going to be cutting through this distributed load, so I'm going to have a small amount of the distributed load spread out over this length dx as well. Okay? So I'm just going to draw it out. Am I making sense to everybody? All of you able to see my writing? People in the back? Okay, thank you. Alright. Here is what I'm going to do. Rather than show this as a distributed load, I'm going to say, okay, hey, I'm slicing through a very, very small distance dx. So, I'm going to say that the distributed load on this portion dx is replaced by a single equivalent force. I'm going to draw that force first. And the magnitude of this force, as you know, if you have a distributed load, what's the magnitude of a force? And you replace it with, it's the area under the distributed loading curve. So for this portion, I'm going to assume, because this is a very, very small slice, that the magnitude of this force is W of x, which is a load intensity, multiplied by dx. So I'm assuming this is some kind of a rectangular distribution. But this is in general, generic. It's not a rectangle, as you can see, it's changing in some kind of a nonlinear fashion. I don't even know what it is doing there. Okay? So this is W of x times dx. So that is replacing the distributed loading over a portion dx. So I'm just going to redraw this figure once again. And W of x dx is acting halfway between one end and the other end, so if you want, that's the length dx by 2. Questions so far? All I'm doing is I'm saying, okay, there's some distributed loading going on from a span of x1 to x2. I'm cutting in between there, taking this little sliver of the beam, drawing its free body diagram. As I'm drawing its free body diagram, I have to account for the sign conventions. So the shear force and the bending moments are drawn according to the sign conventions. And I'm replacing this distributed load by a single equivalent force, which is equal to the area under the distributed loading curve. Then I start summing forces up. You automatically notice that I did not draw any normal force. Okay, so I'm not including the effects of any normal forces here. You're looking purely at the effects of shear and bending moments, shear force and bending moments. So forces in the y direction being 0, here is what I end up getting. Look at that piece here. This is the free body diagram I'm focusing on. So I'm going to have V of x. Then I'm going to have W of x dx pointing down. I'm going to have V of x plus dx pointing down. All of them summed up is equal to 0. I'm going to say that V of x plus dx this is nothing but V of x plus some change in the shear force value, dV. I don't know if this dV is positive or negative. It could be positive, could be negative. Probably the shear force here could be smaller than the shear force there. In effect, it looks like that, right? Because this is acting vertically down. So this has to counterbalance the effect of that, this guy here. But I'm not assuming anything of that sort. I'm just saying this is what the situation is. Do the substitution. V of x cancel off. So I'm left with the following. Okay, so this is V of x all of this put together is equal to 0. And so I end up with the following equation. dV with the negative sign. I'm going to take this guy and bring it onto the right hand side. I'm going to adjust all the signs, make sure you are accounting for it. This is what I'm going to end up getting. Or if I write it in a better manner, I'm going to get dV by dx is equal to minus W of x. I'm going to take off this figure here. What's dV by dx? Yes?
The change in shear force with respect to the distance.
Change in shear force with respect to the distance. What do you call it in geometry?
Slope.
The slope. Fantastic. It's a slope. It's a slope of the shear force diagram. Okay? So it tells me that if I have a distributed loading, the slope of the shear force diagram is equal to the negative value of the load intensity if the load intensity is pointing in the negative y direction. If this was pointing up, my equation there would be dV by dx is equal to plus W of x. Okay? So I'm going to write this down. So first answer. Which tells me that the slope at any point on the shear force diagram is equal to the load intensity value at that point. And mind you, this is for the situation where W of x is pointing vertically down. And we have assumed y-axis to be positive up. If the tables were turned, then dV by dx would be plus W of x. And the same conclusion would hold true. Slope is still the intensity of the load, but with the positive sign. I'll take this piece off as well. Any questions so far? Okay. So here is what I can do. I can now cross multiply. dV is minus W of x dx, as you can see. This was for a distance dx. Now I can integrate this over the entire expanse of the distributed load. So the distributed load starts from x1, goes all the way to x2. Now I can do the integration. This is going to be, because the integrand is dv, it's going to be v of x and v of x plus dx, or v at x1. And then the upper limit is going to be v at x2, okay, because that is the end of the load. Integral w of x dx goes from x1 to x2. I can perform the integration on the left hand side, but not on the right hand side because I don't know w of x. So from the left hand side I end up getting the following. V of x2 minus v of x1 is minus integral my x1 to x2 w of x dx. I'm going to call this as result B. What is integral w of x dx from x1 to x2? If you take the integral of a quantity, what does that imply? It implies that you are looking at the area. You're looking at the area. So in this case, you're looking at the area under the distributed loading curve. So the change in the shear between x1 and x2 is equal to the area under the distributed loading curve. If I don't have a distributed loading, then the change in shear is 0. That's all it says. Okay, so let's write this down and then get cracking on the moments. So B says that the change in the shear is equal to, once again, this holds true for w of x pointing down vertically. If I change the direction of w of x, then this negative sign will be gone. I'll be getting a plus. Okay, so this is area under the distributed load. Distributed load curve. We have to do this once so that we can make use of these conclusions in solving some problems. Okay, so please bear with me as we go through these fairly important results. With your permission, I'm going to take this thing off here. Okay. Usually these are sliding things and one can not keep erasing and walking back and so on. But we work with what we have. Then I look at the bending moment. I have some kind of conclusions that follow suit in terms of how the shear force changes. Then I want to see how the bending moment also changes. So at some moments, I don't know, at one side of the cut, at the right side or the left side. So I'm going to say at the right side of the cut. Right? This is equal to 0. I'm going to say m of x plus dx is m of x plus some small change. Positive or negative change, I don't know. Okay. The problem will tell us what that is. At some moments in the right cut, sign convention. Counterclockwise moments being positive. M of x is clockwise. Look at this. Right hand rule. My palm faces the cut. I curl my fingers into the board. Okay, so this is going to be minus mx. V of x over a distance of dx. Once again clockwise. W of x dx times dx by 2 counterclockwise. So dx times dx is dx square. And then I'm going to have the counterclockwise reaction or the bending moment at the right side of the cut. So that's plus m of x dm. All of these put together is equal to 0. I'm going to get rid of this. Okay. Is everybody done with this portion here? Just very curious, how many of you prefer the chalkboard versus the Zoom lectures? Just a show of hands. Okay. Looks like, we'll see. Okay, I need to consider the opinion of other people who are unable to make it as well. So m of x cancels off. Right? And then I can also do the following. I can say that this dx fellow is really small. So the dx times dx is an even smaller number, and so discard that creature. Because dx is small, so dx square is even smaller. Approximately 0. Okay, so then I end up with the following. So minus v of x dx plus dm is equal to 0. Rearrange the furniture inside that bracket. I get dm is v of x dx. That's all I'm left with there. Or if I write it in a better form, so we get the third result of consequence. dm by dx is equal to v of x. What does this tell me? This tells me that dm by dx, which is the slope at any point in the bending moment curve, is equal to the shear force value at that point in the curve. Okay? So which tells me an even deeper truth. To first draw the bending moment curve, I need to have drawn the shear force diagram. Because I'm getting everything for the shear force from the for the bending moment from the shear force value. Yes.
Why does the W of x times dx over 2 go to 0 again?
Right. So this is dx. Dx is very small, first of all. So if I take a small number and multiply it by itself, it's an even smaller number. So in the approximation that dx, in the limit that dx becomes close to 0, this term becomes really, really tiny. Right. Which is what this statement here says. The dx square is 0. Do you have a question? Okay. All right. So dm by dx is v of x. So this is the slope of this bending moment curve. At any point on the bending moment diagram is equal to the shear force value. At that point. Okay. So one more thing I want to do before I move on to the concentrated forces is if I integrate both sides of this particular equation here, I'm going to get a conclusion similar to what I had for the shear force, kind of expecting the same theme. So integral bending moment at x1 all the way to x2, where the span of the distributed load acts. This is dm is integral x1 to x2 v of x dx, or m at x2 minus m at x1 is equal to integral x1 to x2 v of x dx. So this is the result of D. I'm going to clear off the top half of this one. And without deriving this for the rest of the beam, I'm going to generalize this statement. The change in the bending moment between any 2 points on the beam is equal to the area under the shear force diagram. So integral Vx dx is the area under the shear force diagram. Right? So I'm going to generalize this. Without proving it at any other points, I'm just going to assume this is going to be true, and you can also see that it will be true if you do it. I'll post some lecture notes where we do the derivation on other portions as well. So throughout the beam, the change in bending moment between any 2 points along the beam is equal to the area under the shear force diagram between those 2 points. Area under the shear force diagram between those 2 points. Which is what equation D depicts. So 4 results of consequence so far. I need 2 more, and then we'll be ready to solve some problems. Okay? So bear with me for the last 2. Any questions so far? What are the 4 conclusions? Yes, question. Between. Sorry, that's my shorthand. I'm tired of writing. So the 4 conclusions that we have is, first conclusion: the slope of the shear force diagram at any point is equal to the load intensity, accounting for the sign of the load intensity. If the load intensity is pointed along the negative y, the slope is negative. If the load intensity points along the positive y, the slope is positive. Second conclusion is that the change in shear between any 2 points along the length of the beam is equal to the area under the distributed loading curve. That's the second conclusion that we came up with. Third conclusion is that the slope of the bending moment curve or bending moment diagram at any point is equal to the shear force value. And the last conclusion that we have is that the change in the bending moment value between any 2 points along the length of the beam is equal to the area under the shear force diagram. Okay, so these are all the things that we need. Next stop, go back to this figure here, make a very small cut before and after where the distributed load, where the concentrated load acts. Okay, so make a very small cut. Okay, I'm going to take that piece, draw its free body diagram. All these remain the same, m of x, v of x, m of x plus dm, v of x plus dv, they remain the same. Okay, so this is v of x plus dv here. The only difference is that now my force is acting, instead of a distributed force, it's a concentrated load P, capital P. Sum of forces is equal to 0. Which tells me the following. V of x pointing up, P pointing down, V of x plus dV pointing down. So V of x minus P minus is equal to 0. This is going to be an easy conclusion. V of x minus V of x is gone. dV is equal to minus P. Which tells me, in the limit of this distance dx going to 0, you see, where does a concentrated force act? It acts at a point. It's an anomaly of some sort, right? It's a simplification of a real situation. In reality, there are no point forces. That's kind of oxymoronic. Force has to act on an area. But we idealize this by saying this is acting at a point. So in the limit of this distance dx getting closer and closer and closer to 0, the change in the shear will see a discontinuity. Delta V becomes equal to minus P. Okay, so the change in the shear between that small dx right and left, okay, the shear force diagram. I call it as a shear force diagram or a shear force curve, it's all the same thing. Okay, shear force curve, we'll see